Hello, Math 201. Welcome to today's lecture on uh, the most important theorem in all of calculus, the Fundamental Theorem of Calculus, section 5.3. And so we've been talking up until this point about the idea of the area under a curve. When we gave it a name, it was called the definite integral. And so now we're going to actually define it as a function by making one of the endpoints a variable. And so we're going to define what's called the area function, a of x, and it will give us the net area under some function f of t. So we just use a different variable there and there, so for no confusion. So we make this graph in terms of t, so t, y, and then x is kind of the variable that will be our right endpoint. And so a of x is the definite integral from little a under the function f of t to x. And so a of x, if you plug in an x value, you pick some actual number, it will spit out a number. So it's a function, and it'll spit out the number that gives you the net area under your function. And so this area function is just going to be a nice, clean way for us to describe the relationship between the definite integral and the derivative, which is the main kind of idea of the fundamental theorem of calculus. It links the two most important ideas, the derivative and the integral, together. And so let's talk a little bit about kind of what the area function does. So a of b, capital A of b, means the area from little a to little b, and it gives us that amount of green. And so, and a of a, right, if you start right there, the area from a to a is 0. If you go to b, we've gained some positive area, so our function value is up here. As we go from a to c, we've gained even more positive area, so we go to here. But then as we move past c and start adding this area, that area is negative, so the net area goes down. And so as this function, the area is increasing, and then it gets to a maximum right here, and then the area starts to decrease, or the net area starts to decrease. And so that's why this function over here almost seems like it's the derivative of this function, right? Because when it's positive, the area function's increasing. When it's 0, we have a max, and then when it's negative, we're decreasing. And so that's a key idea, is that the area function seems to almost be related to the original function that we're taking the area under, in that the derivative of the area function is this function up here. So here's the exact definition of the area. So f is a continuous function. Then for any t to the right of a, we can define the area function with left endpoint a as this definite integral. And so let's use that to define, to try some things and compare some area. So they give us this graph. They tell us that this is an area of 27, this area 3, this area 35, and they want us to compute some area functions. And we're going to try doing it with different left endpoints and see what happens. Capital A of x is the definite integral starting at -1. So we start at -1 and go all the way. And then capital F of x is the area function starting at 3. So capital A of 3 is by definition the integral from -1 to 3 f of t dt. And we know what that net area is. The integral from there to there gives us that area, which is 27. So it's -27. And then capital F of 3, well, that's the integral from 3 to 3 f of t dt. And so that's just going to be 0, right? Because we're starting and ending at the same point. A of 5 is the integral from -1 to 5 f of t dt. And so that's going to be this area plus that area, so -27 plus 3. So -27 plus 3, which is -24. And then capital F of 5 is equal to 3 to 5 f of t dt, which is 3. And then C is A of 9, F of 9, so it's the total area. So A of 9 is the integral from -1 to 9 little f of t dt. And so that's just getting this whole net area. So it's -27 plus 3 minus 35. So negative 27 plus 3 minus 35 would be minus 59. Negative 59. And then capital F of 9 is going to be the integral from 3 to 9 f of t dt. And that's going to be 3 minus 35, which equals negative 32. And so we'll notice something about a of 3, f of a of x, and capital F of x. They always differ by the same, those two. They're always differing by the same constant. They're always differing by negative 27. And that's not a coincidence. That's because both area functions actually are an antiderivative for this function. And so they're going to differ by a constant. So capital A of x is that. Capital F of x is that. And so their difference is just a constant. And so that they're actually both antiderivatives, which is the fundamental theorem of calculus. We're going to show that. Okay, let's do one more example with this area function before we get to the proof of the fundamental theorem and the statement. So here's a function, 2t plus 3. So they graph it right here. That's this graph right here, 2t plus 3. And we're integrating from 2 to x. And we want to figure out how a way we can use geometry to calculate this. And so a of 2, the area of 2 is going to be the integral from 2 to 2 of the function, which is 2t plus 3 dt. 2t plus 3 dt, which is equal to 0. A of 5 is going to be the integral from 2 to 5, 2t plus 3 dt, which that's going to equal, it's a trapezoid, right? So that's base 1, that's base 2, and that's the height. So it's 1/2 base 1. Well, what is base 1? It's this function value right here, which is f of 2. F of 2 plus, what's this function value? Well, that's f of 5. And then times the height. Well, what is the height? It's 5 minus 2, which is 3. And so what does that equal? That's 1/2. And then what is the function height at 2? Well, if you plug in 2 into this function, you get 7. Plus, if you plug in 5 into this function, you get 13. Times 3. So that's 10 times 3, it's going to be 30. So the area from 2 to 5 under this function is 30. Find and graph the area function y equals a of x for x greater than or equal to 2. And so how do we calculate a of x? Well, the exact same way we did before. It's the integral from 2 to x, 2t plus 3 dt. But this is the area of the trapezoid. Area of trapezoid from 2 to x. And so that's equal to 1/2. Base 1 is f of 2 plus base 2 is f of x, where we plug in x for the function. And then the height is going to be x minus 2. And so what does that equal to? That's 1/2. Our function, if you plug in 2, is 7. Our function is 2t plus 3. And so this is going to be 2x plus 3, and then times x minus 2. And so if we FOIL and factor this all out, this is going to be 1/2. And then it'll be 2x squared. That becomes a 10, so plus 10x. And then 2x times negative 2 is negative 4x. And then minus 20. And so this is going to become x squared minus, so it'll be plus 6x, so plus 3x. And then it will be minus 10. So x squared plus 3x minus 10. And then, so that's the function. And so that's this right here. So the area function from 2 to x is x squared plus 3x plus 10. This is the graph of that function. And what do we notice is that at 2, it's 0 because the area is 0, and then it's increasing as we go up because the area is increasing as we go up. And there's something else to notice about this too, is that if you take the derivative of a of x, the derivative of a of x is 2x plus 3, but that was little f. So it's the derivative of our area function is actually the function we're taking the area under to begin with. And so that's another way to say this is if a prime of x is f of x, then a of x is an antiderivative of f of x. And so this is the key relationship between the area function and the function we're taking the area under, is that the area function actually is an antiderivative of that function, or said another way, if you take the derivative of the area function, it is the function. And so that is the fundamental theorem of calculus. We want to show that the derivative of the area function is equal to the function we're taking the area under. And so here's the idea. I won't do the entire real proof. I'll give a sketch of it, but here's the idea. You have some function f of t, little f of t. We're taking the area under it from a to x, and then we add a little bit, x plus h. And so we have the area function from a to x plus h, which is capital A of x plus h. And then we have the area function a of x. If we subtract this guy from this guy, what's left over is this little bit right here. And this little bit right here is almost a rectangle. It's not quite, but as h gets really, really, really small, it becomes closer and closer to a rectangle. And so this approximation of it being the function value at x times the width h, this approximation becomes better and better the smaller h gets. And so the idea is that as h goes to 0, this difference is no longer an approximation, it is exact. So the limit, and so that gives us a limit. And so this is where this idea is going to come in. We're going to use that. And so remember the definition of derivative. A prime of x is the limit as h goes to 0, a of x plus h minus a of x over h. That's the definition. So from using that, and so using this from up here, we're going to use that idea from up here. What we can say is that because this is approximately equal to this, you can plug this in right here, right? Or sorry, we can plug this in right here into the limit, and we get that a of x plus h minus a of x over h is really approximately f of x, right? We can say it's approximately f of x by plugging in that substitution right there, and the h's would cancel. And so you get approximately f of x. But this approximation gets better and better as h goes to 0. So thus, if we take the limit as h goes to 0 of both sides, we get a prime of x as f of x. And that's really the whole proof of the fundamental theorem of calculus, is that this approximation, that a of x plus h minus a of x is roughly h times f of x, that approximation, this picture right here, is the entire proof. The idea is take h as it goes to 0, and you get that the limit of this derivative will actually end up being f of x. And so we have the fundamental theorem of calculus. So let's record it. If you have a continuous function on a closed interval and you have an area function that's continuous and differentiable, then the area function satisfies its derivative as f of x. Put another way is that the derivative of the area function, which is d dx, right, because we're taking derivative of x, of the area, right, this is the definition of the area function, the definite integral. The derivative of a definite integral is just the inside function. So d dx, the integral from a to x, f of t dt, is just f of x. This is a lot of ways that people write the first part of the fundamental theorem of calculus. So what is this saying? This is saying that the integration and derivatives undo each other, right? If you take an integral and then take the derivative, you get the original function back, which is kind of crazy. So the derivative and integral are almost inverse operations of each other. And so that's a really, really beautiful thing in and of itself, but it's actually extremely useful too. And so what we're going to do is we're going to use this part 1 of the fundamental theorem of calculus to give us a really easy way to calculate our integrals. And that's going to be part 2. And so this is part 2. Part 2 is this, that if we want to compute a definite integral from a to b f of x dx, then it's just equal to the antiderivative, capital F, evaluated at b, minus the antiderivative calculated at a. where capital F is an antiderivative. So the idea is that if you know how to get the antiderivative of a function, we can compute its area function really, really easy. And so where does this come from? So I'll just kind of do this really quickly, but the idea is this, that if you have the derivative of the area function as f of x by the fundamental theorem of calculus, that means capital A is an antiderivative of f of x, but that means any antiderivative is going to just be off by a constant, right? All antiderivatives differ by a constant. And so capital A of B, by definition, right, is the integral from A to B f of x dx. But what does that equal to? That's just f of B minus C using this formula right here, right? If I plug in B right there and plug in B right there, subtract C to the other side. And so A of B is f of B minus C. But capital F of A, if I plug in A into this, that's A of A plus C. But A of A, right, if you plug in A into here, so plug in A right there, that's 0. So that becomes 0. And so capital F of A is a 0 plus C. So that means the integral from A to B f of x dx is capital F of B minus C by definition, right? Because it is A of B. This thing is equal to A of B. But that's equal to F of B minus F of A because F of A was equal to C. And so that's the proof. And so we get the fundamental theorem of calculus part 2, which is the integral from A to B of f of x dx is capital F of B minus capital F of A. Writing that succinctly, we a lot of times write it like this: capital F of x evaluated from B to A, which means plug in B and then subtract when you plug in A. And so here's some notation. So limits of integrands, that's the integrand. X is the variable of integration. Remember, this is a dummy variable. It doesn't matter. Capital F of B minus capital F of A, that's the antiderivative evaluated at B and A. And then this is the shorthand notation for that. So this is equivalent to this. And a lot of times we'll do that and save time. Okay, so let's do a bunch of definite integrals. So this is the integral from 0 to 10, 60x minus 6x squared dx. And so by the fundamental theorem of calculus, this is equal to the antiderivative evaluated at 10 minus the antiderivative valued at 0. And thankfully, we can do the antiderivative very easy. It's going to be 60, and then it's x squared over 2 minus 6x cubed over 3, and then evaluated from 0 to 10. And so what does that equal to? That would be 30 times 100 minus 2 times 1,000. That's when we evaluated at 10, and then minus 0. And so that's a totally fine answer. We'll just leave it like that. And so that's 3,000 minus 2,000, so it's 1,000, but we can just leave it like that. Let's do this next one. The integral from 4 to 16, 3 square root x dx. Remember, this is just x. This is just x to the 1/2. And so the antiderivative of that is going to be you add 1. So it's 3x to the 3/2, and then divide by 3/2, so times 2/3, and then evaluated from 4 to 16. So that becomes, if you plug in 16 to the 3/2, and then 2 times, and so it's 2 times 16 to the 3/2 minus 2 times 4 to the 3/2, which that's totally fine answer. But if we wanted to simplify, this would be 2, and then 16 to the 3/2 is 4 cubed, which is 64, and then minus 2 cubed, which is 8. And so that's fine. Okay, now the next one, integral of sine 3 sine x from 0 to 2 pi. And so again, by the fundamental theorem of calculus, it's just the antiderivative, which the antiderivative of sine of x is cosine x, negative cosine x. And a way you can always check this is take the derivative of this real quickly and make sure that's equal to that. The derivative of this, right, bring the 3/2 down, cancels with that, subtract 1, you get 1/2. And so that's why it's 3 square root of x. And then the derivative of this, you bring this down, that cancels x, and then bring that down, cancels, and you get 6x squared. And so that works. And the derivative of negative 3 cosine x is 3 sine x. So it checks out, and we evaluate it from 0 to 2 pi. So it's -3 cosine of 2 pi minus, and then -3 cosine of 0, which those are the same thing. This is going to be -3 and then minus, and then this is -3 as well. And so this becomes 0. And so the answer is 0, which makes sense because this area cancels, right? That area cancels with that area. And then finally, let's do this guy. This one's a little bit more complicated, but still using the fundamental theorem of calculus. And so this is way, way better than doing the definition, right? To having to do the limit definition to calculate these areas. This fundamental theorem of calculus really saves us so much work. The way we're going to do this is we're going to simplify this. This is going to be 1/16, 1/4. And then I'm going to break this up into 2 fractions so that I can use the power rule. And so this is going to be t to the -1/2, right? Because if you have 1/2 on top and t on the bottom, it's t to the -1/2. And then this one becomes negative minus 1/t. Or maybe I'll just do t to the -1. T to the -1 dt. And now we can do the antiderivative of that. So add, this one is the power rule, so add 1 to that and then divide. So it's 2t to the 1/2. And then this one is just ln. So minus ln of, technically it's absolute value of t, but everything's positive here, so I don't need the absolute value. And then we're evaluating it from 1/16 to 1/4. And so if I plug in 1/4 there, I get 2 times 1/4 to the 1/2 minus ln of 1/4, and then minus 2 times 1/16 to the 1/2 minus ln of 1/16. And honestly, that's fine. Let's just leave it like that. Because would be all I ask on an exam. All right. So that is using the fundamental theorem of calculus. Let's do some more examples using that. Let's look at this function. So 6x times x plus 1 times x minus 2. And we want to find the net area from -1 to 2 on this. So by definition, the net area is just this, right? I copied it already, and so it's just that. It's just the antiderivative, so that's not hard. So that is just the integral, which is that. And then to do this integral, we just do the antiderivative. And I'm going to do it a little fast, but it's 6/4 x to the 4th minus 6/3 x cubed minus 12/2 x squared, evaluated from -1 to 2. And so whatever that is, that's some number, but we should just plug it in. So 3/2, 2 to the 4th, minus 2, 2 to the 3rd, minus 6, 2 squared, and then minus, let me move this down, let me move this over. Then minus, when you plug in -1, it's 3/2, -1 to the 4th, minus 2, -1 to the 3rd, minus 6, -1 squared. And so that's what the net area is. It'll be some negative number, it looks like, because this area is bigger than that area. How do we find the area, like the total area? So not counting this as negative, how do we find the total area? The total area will be R1 plus, what we do is we integrate this normally, because that will give us a positive. Then we're going to do a separate integral from 0 to 2, and we're going to make it negative, because the value it would spit out would be negative. And so total area is going to equal the integral from -1 to 0 of this function, which is 6x cubed minus 6x squared minus 12x dx. And then minus, the reason we make it minus is because we want to make this positive, because when we do that integral, it would be negative. And so from 0, 0 to 2, 6x cubed minus 6x squared minus 12x dx. And so, for time wise sake, I'll let you do that integral. It's not that hard. It's the same antiderivative here. You just plug in different bounds. And so I think the only difference is that this thing you'd put a minus sign on, and then this one would be the same. And so actually I could do it real quick. It's not hard. It would just be negative. And so negative. So actually the answer would just be this. It would come from that. Oops. Let me do it like this. So it'd be that part, and then it would be minus this part, the 2 part. So that would be the final answer right there, whatever number that is. Because all the parts with zeros go away. And so all it does is it makes that part negative. And so that would be the total area. Okay. Let's revisit the fundamental theorem of calculus part 1 real quick. And so the idea is that if you take the derivative of an area function, which is a definite integral, you just get the inside function. And so for instance, this one, if you just do the derivative and the integral cancel. And so you just get the inside function. And so this is just equal to sine squared of x. For one like this, where the order is off. So one like this where the order is off, how do we do that? Well, we can change the order and make it negative, right? So this is equal to d dx, and then negative the integral from 5 to x square root of t squared plus 1 dt. And so then this negative can just pull out, and then the d dx and that cancel. And so this becomes negative square root of t squared plus 1. Now this one is way more interesting because it's an x squared, not an x. And so how do we do that? And so in order to do that, I already wrote it out because it's kind of long. And so here's the idea. This is the inside function, and we're going to call it f of t. We're going to let capital f of t be an antiderivative of it. And we don't need to calculate it. And so I have no idea what the antiderivative of cosine of t squared is, but you don't need to. We're just going to give it a name and call it capital F of t. So capital F of t, if you take the derivative, is little f of t. Okay, so then taking the derivative of this, d dx from 0 to x squared f of t by the fundamental theorem of calculus part 2 is capital F of t evaluated at x squared and 0, but we're still taking the derivative of it. This, by the fundamental theorem of calculus part 2, is capital F of x squared minus capital F of 0. This is a constant. So if we take the derivative of it, we can take the derivative of these parts separately. The derivative of this guy is by the chain rule, the derivative of the outside function, capital F prime, evaluated at the inside x squared, times the derivative of the inside, which is chain rule. And then this is a constant, so the derivative is 0. And so what we're left with is capital F prime, which is little f, evaluated at x squared, and then times 2x, which is the derivative of the inside function. And so it becomes cosine of x squared squared times 2x. And so the derivative of this thing is 2x times cosine x to the 4th. And so in general, I'll record this for you because it's kind of a cool trick. So if you take if these are functions of x right here, so g of x and h of x, and you want to take the derivative of it, f of t dt, then by the chain rule, it's f of h of x, the top function, times the derivative of that function, minus f of that function, g of x, times the derivative of that function. Okay, let's do one last example. Let's work with area functions. So consider the function f shown in its area is the integral from 0 to any point x for x between 0 and 17. And we're going to assume that all these areas have the same, all these regions have the same area. Based on the graph, do the following. Let's find the zeros. So find the zeros. So A and B really can be combined by making a sign chart. A sign chart for a prime of x, right? If we make making a sign chart for a prime of x, well, I guess that's for b, that's for the local max. So I guess a, let's do that one first. So the zeros of a, so where is the area 0? Well, it's 0 here, and then we increase by r1, we decrease by r2, so it's gonna be 0 again at 8. We increase by r3, decrease by r4, so it's gonna be 0 again at 16. So a of x equals 0 when x is equal to 0, 8, and 16. The reason being is because at 0, we gain positive area, negative area back to 0. Positive area, negative area back to 0. So those are the 3 points. For part B, we're going to make a sign chart. For part B, make sign chart. Sign chart for a prime of x for the derivative, right? In order to find the local max and local min. But that is equal to just f of x, right? And so we make a sign chart for f of x. But the sign chart for f of x is just what is the value of f of x. And so what are the interesting points? 0, 4, 8, 12, 16. So f is positive here, it's negative here, positive here, negative here, positive here. And it's 0, 0, 0, 0, 0. And so it's increasing, decreasing, increasing, decreasing, increasing. And so this is a max, this is a min, and this is a max, and this is a min. So those are the local max and minimum for the area function, right? Not the original function. The original function has max and mins at 2, 6, 10, and 14. But for the area function, its max is at 4, because that's where it's gained the most area. And then it will have a min at 8, because it's back to 0. It's lost the most area. Then I'll have a max again at 12, because it's gained the most area, and a min again at 16. And so that's how we can find the local max and local mins. And then finally, let's sketch a graph using all this information. So using all this information, we know, so I'll do actually know something that make this a lot easier is I'll just borrow this scale. So borrowing his scale, the area function, so it starts at 0, and then it'll increase, and it keeps increasing till it hits a max right there. It hits a max at 4, and then it'll start decreasing until it hits a min at 0, and then it starts increasing again. So maybe I should actually make these a little, so the area looks something like max, min, max, min, something like that. And so this is what the area function looks like. So that's a of x. And so it should be like the derivative of this guy is this function. So when he's 0, when he's 0, the derivative should be flat. When it should be most positive right there. Most positive right there, most negative right here, so on and so forth. And so that's the sketch of a of x. All right, that should be everything you need for section 5.3 in the Fundamental Theorem of Calculus. Have a good one.